Miss Jody here again for physical science. This is our second video. Our last video, I explained what we're going to be trying to do during this time when we're separated, but just as a review, we're going to try to get our notes done. And by getting our notes done, when we get back together, if we're able to spend some time together in May, hopefully, then we can do some of our experiments and have some fun instead of having to try to get all these notes in. So we're trying to do this at home, and hopefully you're following along. Now don't forget when you're doing that to use a half sheet of paper to take your notes, so that way we can glue it right in there underneath the label. I'm going to keep all the labels going in the journal so all the spots are marked, along with any activities that I send for you to do. Now, just to make it a little more exciting throughout the lessons, I'm gonna try to come up with little activities that you could do at home too, like maybe some type of craft or something that would go on the next page. This topic is a little hard to do with that being the nuclear forces and stuff, but if there's anything I can come up with, and I can send you a video on how to do it or a link or something like that, and then that way you won't be constantly just having to do notes and watch videos. But of course, we're blessed to have the video process because there's a lot of very talented scientists that have put together some great videos, way better than me and my little notepad here, or my little journal notes, but those can be helpful to, again, visualize some of these things when we're not able to be together and do our experiments and look at the visuals. Okay, so don't forget to do that, and what you should do is write the title of the topic, like the strong force, on the back of the note sheet. That way when I glue them together, I can easily put them in and not lose track of which note goes with which one. And also, if we go too long, I'm going to have like a drop-off spot, I think, here at the Science Center, because I'm here every day, and you could, whenever you're out getting groceries or something, maybe every couple weeks or something, you could drop it off in a drop box if I made one. That way I could keep up with the journals, so that would be an option too. Obviously not something you'd have to do, but if you were out. Obviously, we shouldn't be going out, but if your parents are out, they could drop it off. Okay, so our strong force. So last lesson was on the weak force, and so this will be ending our topic on the 4 fundamental forces: the gravitational force, the electromagnetic force, the weak force, and the strong force. Now, of course, if you remember the weak force, it was way too complicated to get into, like how the full end of the weak force, and I would send you a video, but I don't want to overwhelm you with all of those aspects and all of those particles and trying to memorize all of those, and the regular particles and the antiparticles and how all they work. So we did just focus on just the fact that the weak force helps with the process of radioactive decay. Hopefully you enjoyed watching those videos on understanding those aspects of radioactive decay. Now this last one, the strong force, I'm also only going to give you a small little dose of, and our book doesn't go that much into it. It just is introducing these, and that's because later on, if you take a physics class, obviously this being physical science, you're just being introduced to the physical science world, the physical world, like we're seeing all these processes. But later on, you would have to learn this in more depth. So. But that's kind of nice for us because we can just get introduced to the topic. Okay, so the strong force. So what is the strong force? So the idea behind the strong force is that when we look at, and we've already looked at the electromagnetic world, and we understand how it's governed by the attractive repulsion, the attraction and the repulsion of charges. So let's say we have 2 positive charges. When we have 2 positive charges, if we bring them together, they'd repel, right? And under normal conditions. And so under normal conditions, that would be the law of the 2 charges that are similar repelling each other. And then of course if they would be opposite, then they would attract. Now when we look at these 2 positives and the fact that they should be repelling each other in normal conditions, there's an area of our understanding where instead of repelling, they are next to each other, and that is in the nucleus of the atom in the models that we have. So this is a terrible model. It's a Bohr model, which isn't accurate, but just for our understanding, since we've been using those for counting. So in the middle, my nucleus of my atom, I have a whole bunch of positives sticking together, which in reality, they should repel. And so the questions begin to arise, why is this? Why would all the protons stick together if the rule is 2 positives would repulse each other? And so that's when the idea of the strong force came into play. And so in physics, the scientists that were working with this, they came up with the idea that there had to be a short range attractive force pulling them together, which we would call the strong nuclear force. And this strong force would have to be so strong that it would overcome any other force that would be acting upon the center of that nucleus. So we would have the trying to repel apart, and then even there's the force of just the regular gravitational force that would be trying to pull them together. So you'd have to overcome that pulling together, which would kind of help you with your problem, and then that repulsion. So any force that would be acting on this would have to be stronger. Therefore, it's called, obviously, the strong force. So with the strong force, in 1935, this gentleman, Hideki Yukawa, I don't know if I pronounced that right, proposed that this force occurs as a result of the fact that protons and neutrons can exchange tiny particles with one another. He called these particles pions back in the day, and he actually made a prediction of what their mass should be. And so he was doing some experimenting and some calculating too, not just coming up with like, let me come up and make up some cool idea that there's this mysterious force holding the centers together. And so he began to experiment. In 1947, these pions, that he had called them, were actually discovered by an experiment, a different experiment, and their mass was indeed roughly what this gentleman had predicted. And so when they were experimenting and they figured out the mass of these little tiny particles, then he was correct. He was close. They were almost exactly what had been predicted. And so this won the Nobel Prize in 1949 because of this particular discovery. So the world of the strong force began to be looked at, and of course before there was already some theories between the other forces that possibly the reason they behaved the way that they did was that there was an exchange of particles. And so this brought us into the smaller particle world, and we already had the regular the theories of the atom, then when we used to think it was all just one thing and it was indivisible. And then when we realized, oh no, wait, there are protons, there are neutrons, there are electrons, and so they became subatomic particles. So instead of just the atom being one, the atom was made of littler particles. And then of course now in particle physics, we have all of these things and all these extra little particles, some that make up like some of the particles, some that are cousins of the other particles, and there's all these, antiparticles, and I mean, it's just crazy, and you really have to be interested in studying particle physics to really sit down and kind of map it all out and figure out every particle and how it all works and all their spins and all that crazy stuff. And so with our topic, though, it's just getting us interested in the idea of the particles being possibly why these forces work the way they do. And we saw that when we were looking at the gravitational force. Do you remember? They were talking about the theory of the graviton theory, and that these gravitons were little particles that were being exchanged back and forth, and that was causing the force of gravity, one of those particular gravity theories. Remember, we had the different gravity theory between Newtonian gravity and then Einstein's theory of gravity. And so it was about particles. And then we also talked about this when we were looking at the electromagnetic force, that these exchange of particles, instead of being gravitons with gravity, but they were the photons, the light packets of energy. So when we see these ideas of particles being exchanged, creating a force, there's one in each one of the particular fundamental forces. There's a particle exchange theory. And so with the strong nuclear force, we have the protons and the neutrons that are in the center of the nucleus. The idea is that these little pions can be exchanged between the two, and so like a proton, if he wanted to make a pion, a little particle, he'd take a little bit of his energy and create a little energy packet that could be exchanged between the neutron and vice versa. And that would be this pooling together and making them as they exchange. And we didn't get a chance to do the lab that was back in the gravity unit when it talked about the exchange of particles, but if you remember reading, it said to take two people and have them stand a little far away from each other and throw a ball back and forth and then time them. And you were supposed to be timing, and as you threw the ball back and forth, you kind of start moving towards each other, especially when the ball's a little shorter, back and forth, back and forth, back and forth. You keep moving towards each other. And that was the idea of the exchanging of particles, like the exchanging of the ball. It makes you as you have smaller distances, you keep moving closer in, and it's pulling you together, that exchanging of that ball back and forth, back and forth, back and forth. And so that's that idea, an analogy to kind of visualize that. And so these guys exchanging particles back and forth and pulling each other. Now, the strong nuclear force, when people talk about this, they say, well, if this force is so strong that it ends up being pulling these two together, why wouldn't it be, and it's stronger than the electromagnetic force, and it's stronger than gravity, it's stronger than everything else, then why wouldn't it just pull everything towards the center and like make, every thing in the entire world become this big giant nucleus pulling it together? And the idea is that it's only going to be working over a short range. So this particular force can't just happen on a regular basis when something's very spread apart, but it only acts when the actual particles come together and they're in such close distance. And somebody illustrated it or said it was kind of like Velcro. And I think one of the videos I'm going to attach, I think that gentleman describes it as Velcro, but somebody, if it's not in there, somebody described it as Velcro. Velcro has no pull, right, at all when it's separated. But the moment they touch, then it's very, very strong. And so they illustrated it like that. When these two things are together, the protons or the neutrons, or proton to proton, when they're together and they've got that little exchange, just think of it as like the hook of the Velcro, and the exchange going back and forth, it creates a very strong situation. But that can only happen when they're actually so close they're touching. And so if you pull the protons farther away, the strong force is not active there. And then, so instead, then you'd have your repulsion away from each other. So the strong force would only be in this very, very short range of the particles touching each other so close that it's hard to even illustrate that small of a distance. And so the strong force is what scientists are saying keeping the nucleus together, either proton to proton or even proton to neutron, and making everything stick. But then it's also illustrated that this strong force also is what's making the proton itself stick together, because the idea is that protons are made of other things called quarks, and neutrons being made of other things too, and that they are exchanging particles called gluons, gluing them together, and the strong force is helping them stay together also. So there's a lot of cool things in the particle exchange type theories. And you can see that in the electromagnetic force, the strong nuclear force. And then even when you start studying the weak force, there's a whole bunch going on there with the weak force in between who's interacting with who. And so as an introduction to the strong force, this gives us an idea that this would be a super strong force holding the center of the atoms together so that they don't explode and so that they can be what they are to create the whole rest of the world that we see in the world we call matter. You, this table, this pencil, everything. And so if these things were flying apart, then we have nothing, right? We got to have something that keeps them together, and that's the whole existence of everything else that we see. If that didn't exist, this super strong force, whatever it really is truly, is the way that our world exists. Okay, so I don't have anything really creative right now for the book to add to you, but I'll look around and see if I can find something creative, craft or something that we could put here to illustrate this, just so we have something that's not just boring old notes, right? All right, so I hope you're doing well. That's the end of chapter, 13, I think we're on. And so I'm going to have to figure out a way to do the tests. I don't know exactly how I'm going to do that. Just have you print them out and do them at home or what. because it looks like we're going to be separated for a little bit. But don't forget that as you're going along also, let me find it, to still be doing your study guides. And you can, if you want, you can send those to me. You could do those digitally and save them as a PDF and send them to me, and I could grade them and print them out here. Or if you just want to do it like on regular notebook paper like you have been and save them for either a time when I do the drop-off box, or if we get back together and I can just then grade them all at once, okay? So still be working on your study guide at the end of each chapter. And we're a little bit behind now that everything's happened, and so I'm going to just keep making videos topic after topic, and it'll go a little longer than on our regular syllabus, but that's okay. That way you can just slowly keep at it. And we have what, 16 chapters, I think it is, altogether. And we were the only class of all of my however many classes that was actually on target until all this happened. So we're a little bit behind now, but that's okay. After this chapter, I want you to go ahead and continue on to the next chapter, and I'll keep making the videos. And I hope to see you soon.